Yes, sir. We are live now, sir.
All right, thank you. Thank you. I think, yeah, let's get started. I think there's one student here. Anybody has any questions? You can just feel free to chat or type in the chat. Oh, I see. Hello. Hello, all. If you have any questions, please feel free to type in on the chat. I think this session was quite delayed. It should have been much sooner. Any questions? Right. Kushagra or Nikhil, can you just see in the sheet if you have any questions?
Yes, sir.
Yes, sir.
Please read out if you have anything. Or even from the forums, right? If you find anything interesting that we should clarify, there's a doubt or something that students are facing, we can do that.
Sir, one question is there in this. He's asking about the pinch-off effect in MOSFET.
Okay.
So he's saying it can't be explained using depletion with extension due to reverse bias in drain channel region.
Let's look at it, okay, carefully. I mean, so what we are saying is you're talking of a MOSFET. So let's take a N-channel MOSFET. So N plus regions, source drains, and there's a channel, right? This is the linear region where you have a channel which is N plus, N-type channel, right? And then on the top, of course, we have the standard oxide and then the gate. This is the gate and this is oxide, right? And then the substrate will be, let's say, p-type. This is what you have, correct? So now the question is, what is pinch off, correct? Pinch off is essentially when your channel is getting restricted, right? So in this picture here, there is one small thing that we have to notice. This inversion charge, right, that you are showing here. It's a very, very thin layer of inversion charge. It will be hardly less than few nanometers, right? Approximately nanometers, let's say 3 to 5 nanometers or something like that. It's a very small region. It looks like it's very big, but it is typically very small region of space. If you look at the actual solutions of inversion charge densities that are there on the slides, you will see that the distance is very, very small. Okay. So now what is pinch off? Initially, when your gate voltage is small, or rather, let's see this. What are the conditions? Can somebody answer this? Let's try to make it a little interactive so that I also understand where the understanding is a little bit lacking, so that we can make it better. Yeah. Does anybody want to answer? Does pinch off occur at low VDS or large VDS? That's the question.
Hello, is it audible?
Sharad, yes. Hi. Yeah,
Hi,
you're
sir.
audible.
Yeah, actually, I only posted this question.
Okay.
So, for pinch off, VDS should be larger than
VDS should be large, right? Yeah.
Yeah.
So pinch off occurs when VDS is large. Let's assume it is almost equal to VDD. Okay. Now, why does this happen at this point and not at low VDS? Okay. So, to understand this, we need to look at a MOSFET as a series of capacitors, right? So basically, when your voltage is less here, ground, and this is VDS. Okay. Let's initially assume that this is only 50 millivolts. Okay. So, what will be the voltage across the channel? How will the voltage across the channel be? Sharath?
Yes, sir.
So what should happen? I mean, if you have a, how will the voltage be distributed across this?
Uh, so it will depend on VDS also, right, sir?
Yes, correct. So now
Yes.
what we are saying is this is almost like a metal, right? This
Okay.
is like a
Yes,
metal,
sir.
large, high doping, right?
Yes,
There's
sir.
a slightly lower amount of doping here, whatever, the inversion charge here. But there is a drop of VDS across this, isn't it?
Exactly. Yes.
Yeah. Okay, first let us consider one scenario. Let's take it step by step. Let's take one scenario. And let's say first you have depleted this. Okay. You have a depletion region here. You have not yet inverted it. Okay. So you have applied a voltage and you have depleted it. Now, there is a this is a kind of a resistor, right? It's just a semiconductor, piece of semiconductor across which you have a 50 millivolts voltage. So, in effect, if I have to draw the potential across from the source to drain, source, and this is a drain, if you have to draw potential, it will be like 50 millivolts. This is the voltage drop across the channel, right? VDS, isn't it?
Okay. Yes,
So
sir.
now this side is essentially grounded. Other side you have a small VDS. So in effect, you have a almost a very small voltage across the channel, right? So it's as good as almost a very small voltage across the channel because this is only 50 millivolts at the small voltage, right? Now, what happens when you apply a gate voltage, right? So you can think of this entire capacitor as, basically everything is, it's an area, right? If you look at it from the top perspective, it will be like this will be an oxide. Below, there will be a metal gate on top of it, right? This is the top view I'm trying to show you. And then you apply the voltage across it, and the voltage falls across this oxide. And what happens in this region below the oxide is what we need to understand. Okay. So now essentially what you have is your gate voltage, VGS, VG, right? And then the source is basically this is source voltage. Now the voltage, you can think of this entire region of the gate as a series of capacitors. Okay. So let me try to put that, which is this. Okay, this one. Let me take this out and then say that. So this is my oxide. Think of a tiny capacitor like this, a series of capacitors. They're all in parallel, right? It's just one large capacitor. Now, if you think about it like this, so essentially this side of it is 0. This side is 50 millivolts, correct? So now, locally, what is the overdrive, gate overdrive? Okay. So locally, what is the voltage across the capacitor is what we need to look at. Okay. Let me make it for simplicity. Okay, yeah, it's fine. This is okay. So I have 5 capacitors, right? So essentially, I can say that this is about 50 millivolts. So this is 10 millivolts, 20 millivolts here, 30 millivolts here, 40 millivolts, and 50. Okay, 50 overall. Okay, let me do this. Okay, with me so far, Sharath? Sharath?
Yes, sir. Yes, sir.
Yeah. So what we're trying to say is this voltage is getting distributed across the channel, correct?
Yes, sir.
So now you have a metal on the top. This is a metal, correct? So what is a VGS now, right? The condition for inversion charge to be produced is that VGS should be greater than VT. Okay, as a first approximation. Okay, so now what happens is when this voltage is small, effectively, you have the entire channel having the same amount of VGS minus VT. Is it making sense? So what I'm trying to say is, okay, let's look at this point, okay? At this 10 millivolts point. Okay, my gate voltage I have applied is 1 volt. VG is equal to 1 volt I apply. Okay, now what is the voltage across this capacitor? It is 1 volt minus 10 millivolts. Correct?
Okay. Okay.
This is effectively what you have here. But if you come to this side of it, it is 1 volt minus 1 volt minus 50 millivolts here. And this is 1 volt minus 10 millivolts. Correct? Locally.
Okay, sir.
So when let's say VT is only 0.7 volts, then all the channel everywhere you have almost, if I assume that VT equal to 0.7 in this case, the whole all the region under the gate, this entire region will be inverted. Correct? Makes sense? When VGS is small. Now the story changes when VDS is large. Okay. So again, I'll do the same thing here. Okay. Copy. So now what I will do is the same situation, except that I'll modify my drain voltage. Instead of this, let me make it 1 volt. Okay, I want it to be 1 volt here. So, okay, if I make it 1 volt, now what is my voltage across the channel? Here it will be 0.2 volts, 0.4, 0.6, 0.8 and 1 volt. Correct? There's a voltage drop across the channel. And now, locally, what is the gate voltage? What is the voltage here? So here VG, you are applying is 1 volt again, the same thing. Okay. Now, at this point on the left side here, my effective voltage is what? VG minus this voltage. Let's call this as Vx. Okay. So let me take this as Vs equal to 0. This is VDS, right? Equal to 1 volt. But in between the channel, your voltage is something in between. Let's call it some Vx. Okay, that is varying across it. I'm assuming that it's linearly varying. Okay, it may or may not be the case, but let's assume that for a moment. Okay, so now what happens is at this point, what is Vg minus Vx? Vg minus Vx will be
0.8.
0.8 volts. Similarly, here it will be 0.6 volts. Here it will be 0.4 volts and 0.2, and here it is 0. I'm exaggerating this, okay? This is not, this is 0 volts. I'm really exaggerating the picture, but just to show you what it is, right? So now, locally here, you will have a channel forming because VGX is greater than VT. There's no problem here. But the moment I come here, I don't have an excess voltage of 0.7 here, right? It's only 0.6 now. VG minus Vx is only 0.6, which is less than 0.7. So I won't have a channel here, right? Or I won't have electrons here. No inversion. Why am I pointing this? This is no inversion. Here I have inversion. Follow what I'm saying? It gets a little bit more involved, but as a first approximation, is this making sense?
Yes,
Because
sir.
I have a VDS across the channel, the effective voltage across oxide is different from what you're applying at the gate voltage. Okay. Now, this is not as dramatic as this is. In the actual case, if you have a transistor, this will not be so dramatic. But what you'll end up with is have a oxide like this. You essentially have a region. We are trying to now show that there is towards the drain side, the voltage across the oxide is not sufficient to cause inversion. Okay. So this part, what we are saying is voltage at gate not sufficient to cause inversion. Okay. So this is what we are calling as pinch off. Okay. So in effect, even though this is shown as a linear variation of inversion charge, it's not quite. Yeah, there is some decrease in density, but essentially at some region, till some region you have some inversion charge, and then there is a region of space where it is not, there is no inversion charge. Is this making sense so far? So there should be a pinch off.
Yes, sir.
Now the question is, at what voltage will this occur? Pinch off. Okay. This is VDS. Okay. Initially, we saw that there is no pinch off. If your VGS, if VDS equal to VGS minus VT, what happens? Okay. If you assume this is the situation voltage you apply, what will happen? This is a source side. So what you will see is the voltage applied here, it is VG, right? This is VG on the top. So at this point, your VG at the edge of the inversion charge, right? Where the pinch off is just occurring. Or when the voltage is VGS minus VT. Let's try to compute. It is my voltage at this point, okay? At the edge of the drain, right? So this will be VG minus, it will be VGS minus VT. Or VGS, both are same essentially. Okay, in this case, because you are applying reference as a source voltage, minus VT. Okay. If you consider this, this will be your Vx, right, at the drain end, which is equal to VDS. Okay, and this is VG. So what is happening is this is turning out to be equal to VT. So when your VDS is exactly equal to VGS minus VT, you will just have inverted this point. Okay, this edge is just inverted, just enough to cause inversion. Now, if your gate voltage is bigger than this, okay, sorry, not gate voltage, drain voltage. If VDS is greater than VGS minus VT, okay, then this will be shifted to the left, and you will have pinch off. Does this make sense?
Yes, it is clear to me. I have one doubt, sir.
Yeah.
Shall I ask, sir?
Yeah, please.
Yeah. Sir, here we are not discussing about the that the drain to body junction is getting reverse bias. So what will be the effect of that depletion region on the channel charge?
Gate to body.
No, sir, not gate to body, drain to body. Well, drain to body junction will be there, right?
Right.
So we are applying positive voltage to drain.
Okay.
And let's say if our body is grounded, so there is also PN junction is there, right?
Right.
Drain to body. So there will be, if we are applying positive voltage to drain,
yeah,
and if body is grounded,
yeah,
then that PN junction is reverse bias.
Correct.
So there
Correct.
will also be a depletion region. So
Correct.
how
Yep.
that would affect the channel charge? That is my question.
Oh, okay.
Now,
so this is okay. So that okay. So now this is a very important. Sorry. Yeah. Continue.
Yeah. This was my question, that how pinch off occurs. But now after listening to your explanation again, I got the doubt. Then how the depletion region will actually influence the inversion charge?
Of course it does, right? So now for that, there's something called short channel effect, right? VT. There, I think week 10 maybe I would have discussed it, or just
okay, sir. I have just till now I've covered 9 only.
Okay, so the 10th one I think it will be there, wherein we talk about what happens this here, right? This is what you're asking. There's a depletion here. Exactly. This is N plus and this is P. This is a depletion region. Now, when you're the same thing on this is ground. So if this is ground, nothing much happens here. But there'll still be a small depletion region here also, because this is N and this is P, right? It doesn't have to be reverse biased also, correct?
Okay, yes, sir.
This is ground and this is this is ground. Both sides are ground,
but both will be
NP.
Grounded.
Yeah, two will be grounded, but still there will be built-in put a depletion region there, right? So now what happens is, if you have here this, let's call it XD, X depletion region, right?
Yes.
Distance. Now, when your channel length is much larger than XD, Okay, nothing much happens. Okay, you are anyway, gate is causing the depletion here first, right? All of this is getting depleted, correct? Because of the gate.
Yes, sir.
When you turn on the gate, all of it is getting depleted. Now, this part is because of the drain, this small region here at the edge. This is because of the drain, correct? When a length is larger than xg, nothing much happens. Okay, but if you change your length, right? If you go down to sub-micron MOSFETs, let's say this length, we now I think L less than 1 micron, we call it sub-micron MOSFETs. Okay, this I think was, let's say, around 130 nanometers or something like that. Well, not even 130, even before that. Okay, 180 also, it's much less than 1 micron. So what's happening is, when your L is less than this, your VT should change. How do you think it changes? You're right that VT will change. But how will it change? VT will increase, VT will decrease. Think of...
VT should increase, right?
No, it should... Okay, think about it. VT is a voltage that you're applying on the gate to cause the depletion and then inversion charge to come in, right?
Okay.
Now, your job is becoming easier. When you go to submicron MOSFETs, without any gate...
Okay, you have to apply less gate voltage.
Yes, because already this part is depleted. Part of the channel is already depleted, right?
Okay, yes.
Right? Your impact of the drain depletion region is much larger. Correct?
Yes.
So you don't have to deplete. You only have to deplete the rest of it here. So your VT will reduce. Okay?
Yes. Okay.
So I can plot out my VT. I think this is what we'll show in the lectures there. As L is becoming smaller, this is L, channel length. Initially, it will be flat, no effect of channel length. But then after pump, sorry, that should not. It's like this. It starts reducing. VT will start reducing. Okay? This I'll discuss in the week 10, I think.
Okay, sir. Okay.
Yeah. And there's also something else called narrow body effect. Slightly more difficult to imagine, but do try to give it and see what it is. Okay, the VT will actually increase when you have a narrow body.
Narrow body means like we are talking about SOI or kind of thing?
No. Narrow body means your width, right? W by L is what you care, right? Width of the transistor. Let me try to see if I can pull up that. These things are very old now. I don't know if these are the actual ones. Channel. That's exactly what I will talk about, short channel effects. What happens to VT, right? It's okay. Narrow channel. This is wide channel, this is short channel, yeah. So as I'm saying, your VDS is large, your VT will actually dramatically drop. If your VDS is small, okay, there is some drop. Basically, what is the width of your drain depletion region? Okay, this is what I'll explain here, the details of it. And then the other thing is, your transistor will have two parts, no? You have a better picture than this. Long time since I saw these things. This one. Look at this. So you have two things. One is the length of this channel length and the width of the transistor, right? This is the W. Okay.
Yes, sir.
But then if this is narrow, this is small, width is small, then what happens is this is not quite only this, but there is a surrounding, this side also there will be some depletion regions on the side. Okay.
Yes.
When you apply gate voltage, you're not only inverting across the width of it, but the slight over, there will be a slight additional depletion that has to be, the region that has to be depleted here. On the left and right is what you are seeing, and this top and, I don't know, this is north and south sides also, right? You have to deplete an additional region. Now, what happens is if you go to narrow channels, that part will be significant. So this additional depletion that you are causing, this is a width you're seeing, no? So along
yes,
the
sir.
width, this under the isolation regions also, you have some additional depletion that you have to cause outside that. Now, when your width is very large, it doesn't matter. But when you go to smaller depletion region, this additional depletion that you're causing, that is not directly contributing to your current conduction. Right? That is also there. So this will be larger. And because of which, as you reduce the width, the VT increases. Okay? So short channel effects and narrow channel effects. There are two of these things that come up. Yeah. And this is quite, I mean, this is very important and actually very, very very, very important for design, because when you're designing a transistor, what we're teaching in this course is very, very simple. W by L is this much and all that, right? Simple first square law model. But very soon you'll see that in the for 25 years at least, right? Even more than 25 years, the transistors don't exactly behave as what we are describing. So short channel effects and all I described is one part of it, but there are a lot of other effects that come into picture. So what you end up doing is you build spice models for different categories. You basically bin your devices into some different length bins, right, and width bins. You try to characterize and understand the device performance, and you build different models for different scales of devices. That's how you try to make your designs accurate. It's an extremely important part, which is done using what we call as compact modeling.
Okay.
Yep. Anyway, good. Anything else? Kushagra, there was something else, no?
Yes, sir.
Jobs or
was his
something?
question only.
Huh?
I think
Yes,
it was
sir.
his question only, sir.
Question only, sir. He wants to do research in GaN-based RF amps.
Amps, okay.
So he is asking, how should I move further after taking this course? Besides heterojunction principles, what are the differentiation in these? He is asking what are the difference in heterojunction principles and 2DEG. Right.
Okay, 2D
Sir,
electron.
sir, yeah, actually, I am planning to work in RF GaN HEMT.
Okay.
So I have taken this basic course. Sir, I understood that we are teaching here MOSFET, but I am interested in, let's say, if I have to work in HEMT, then what should be my way forward after taking this course, after finishing this course, I meant. Because
HEMT essentially is a heterostructure, right? With different semiconductors, you form these thin layers, and so I mean, a lot of optoelectronic device courses will also talk about the physics of all these 3 phi's and different layers and so on. That is one thing. But if you are specifically interested in RF, basically for high power you would need GaN. Correct? You understand that?
Yes, sir.
Why?
Yes, sir.
Why? Why GaN is useful for high power?
Yes, sir.
No, I'm asking you a question. Why
is it a question?
Yeah.
Sir, GaN, because it has a higher band gap. So it has band gap of 3.4 electron volt.
Correct.
And because of this higher band gap, it will have higher breakdown voltage. And ultimately you can use it at a higher voltage, higher power.
Power devices, yeah. For all this EVs and all that, right? For electron.
Yes, sir. Right, sir.
So there the question.
My interest is working on RF as well as power. So it is high frequency and high power I wanted to work on.
Yeah.
Particularly, I'm targeting X band and above, maybe KU band or Ka band or so.
What are you doing right now?
Sir, I am working. Actually, I am a PhD scholar in IIT Gandhinagar right now.
Okay.
So it is part-time, but actually I am scientist in ISRO.
Okay.
So yeah, so it is, basically it is related to satellite communication.
I see. Got it.
So yeah, that is the purpose.
Okay. So,
So my question was that, I am already taking this course.
mhm,
So how should I extend it? I am already working on it, sir.
mhm,
But theoretically, there is some gaps that I wanted to fill it.
mhm.
So I just wanted to know how should I go further? Like after taking this course, what should be my next step so that it will help my PhD also,
Mm.
and you know because I understand about heterojunction and all those things, like how to is formed and all those things.
Mhm.
So the question is that after taking this course, what should be my way forward for taking hemp and understanding theoretically it.
Okay. Hemp, I'm not certain. I mean, there'll be some specialized textbooks that will talk about it. I'm not certain of a course, I mean, which is talking of, maybe there is some optoelectronic devices course.
Okay, sir.
For example, Professor Shenoy's course is there on NPTEL only, IIT
Mhm.
Delhi, Professor Shenoy. He has an
Mhm.
excellent course on semiconductor optoelectronic devices. Okay.
Mhm.
Some sections of it will deal with the physics of HEMS and all that. Not,
Mhm.
I'm not certain if he talks of HEMS, but at least the 2D electron gas formations and all that. Okay.
Okay.
You can pick and choose. You don't have to
Mhm.
see everything, but you can pick and choose. But the way he explains it is very, very nice. Okay. That is
Mhm.
one.
Mhm.
There
Mhm.
could be some other specialized courses like that. But for your research, I mean, yeah, once you understand how the heterostructures are formed, right? It becomes
Mhm.
slightly more difficult to predict the bands in that because you have these band offsets which are you have to know experimentally or something. Right? You have to have that valence band offset, conduction band offset, how much it is to draw your band
Mhm.
diagrams. It becomes slightly trickier, but
Mhm.
it could be I mean, it could be a useful thing if you're going into these devices to actually simulate them in, let's say, some TCAD tools.
Mhm.
That's much more easier to do, right?
Okay.
Once you understand how the device operates and functions in the silicon,
Mhm.
you can
Mhm.
simulate some of these things in TCAD, and then you can try to understand the device. You'll understand similar things. There'll be some
Okay.
nuances about it. And
Mhm.
in terms of RF devices, I'm not very certain. Okay, if there is anything special, like you need a power amplifier, and that will
Right,
be
sir.
similar in design, right? But only thing is, if you go to GaN, you may not have both the N and the P transistors very easily. So you have to
Yeah.
choose because your technology itself is still developing,
Yeah. Yeah.
right? So those limitations will be there. But yeah,
Yeah.
you have now foundries that are actually giving you some GaN devices.
Mhm.
So yeah, that should be possible. So you're
Okay.
trying to tape out some chips on GaN.
Sorry, sir.
You're trying to do some tape out of chips on GaN for your RF applications.
Yes, sir. That is the plan actually.
Okay.
Not tape out. Actually, we have fabrication facility also.
Mm-hmm.
So yeah,
Okay.
we are trying to get the devices actually. So it will be basically NMOS only
Mm-hmm.
and depletion type only.
Okay. Yeah.
So yeah.
Yeah. So I mean, you could. Yeah. One thing is to learn those things and try to take the foundry model and then try to play with it and see.
Okay. Okay. Yeah. Okay.
TCAD,
That
TCAD
is a
will be
good.
something useful, I think. TCAD
Yeah.
simulation
Yeah. That
in
is a good
$30.
idea, sir.
Yeah.
Even we have some foundry models also, but that would be, really, it is a good idea. Yeah.
Yeah.
To start with.
Because I mean, you'll understand the device part of it, but once you have a foundry model, yeah, that's it. Rest of it is it's not it.
Okay, sir. Okay. Yeah.
Uh, Good. So there's one more question. No, this student on how to get into semiconductors.
Yes, sir.
Yes, sir.
Okay.
So
I,
she is
hmm.
asking that
That's a
she's
general
finding it a
question.
bit challenge to keep up with this course. So how she could do it effectively?
And
uh,
also she wants to plan some career in semiconductor. She want to do MTech in EC or gaining an experience, which would be good.
MTech will always be good. Okay, unless because see there is some you when you're doing BTech, you'll touch upon these concepts, but you'll not really go into the depth of it. Semiconductors need a little bit more focused understanding of different aspects, right? The typical EC curriculum or EE curriculum may not cover it in all. So MTech will always be helpful, okay? Because there are three major aspects of semiconductors. That is the devices part of it, which this course is talking about partly. We're just scratching the surface. There's a lot more that can be learned in all these things. And then there is a design part of it, which I don't think we even do it, right? I mean, there are some courses, various design courses that touch upon how the CMOS circuits are designed and so on, right? Inverters, adders, and all that. And the last part of it is technology, the actual fabrication part of it, which is again a lot of different things are there. And okay, if I have to name a fourth one, more of advanced technology. Whatever you learn in these textbooks and courses is limited. What's happening right now is pretty advanced. So you have to get a flavor of the advanced recent happening in the last 10-15 years. That's also important. So these things will not be covered in a regular BTech curriculum. So if you want a semiconductor focused career, I would suggest you to do an MTech degree, if not a PhD. Okay, that is one thing. Now, coming to the point that this course videos are, you're finding it difficult to keep up, you should not be surprised by that, because, I mean, I myself have taken these courses 3-4 times, right? First time when I take in my undergraduate time, okay, I think I understood, but then I realized after some time that I don't fully understand it. Again, you take a similar course in masters, again it happens, again some other time. Only when I start teaching these courses, then I start understanding a little bit better. Okay, so this is natural, it will happen. Don't worry about it. Try to understand bits and pieces. Try to get a physical indication. Don't worry about the exams too much. Try to understand what, if you're able to explain this to, let's say, your friend, right? Then you have understood it. When you start explaining, you start realizing what all you don't understand. Okay, so that is a good way of trying to do it. And don't worry about all the details that I talk about in the lectures. Focus on the assignments. Especially, I think there was a question on how to prepare for the exam. NPTEL is now nicely saying that I think, I don't know, 30 to 40% of the questions are based on assignments, right? Or 50%, and then there is another 10-15% or 20% of it is based on recall. Just whatever was discussed in the lecture videos. Only about 10 to 15% are open questions, I think, right? Completely new. That also does, we don't really do completely new questions. So don't worry about the exam too much. If you have taken all the assignments and try to solve them, and then you'll be able to do an exam well. There's no problem with that. Okay. A lot of questions, I mean, we really are not trying to do new questions in the assignments, right? Or in the exams also, we tweak them a little bit, not really completely new questions, right? We are not really here to make sure that you understand all of semiconductors. It's not possible in this kind of an online kind of a course, right? Unless you have a regular interaction with your instructor and all that, these things are challenging. I understand that. So don't worry about the exam too much. Just focus on the assignments, do them well, understand what is being discussed, ask questions. There are a number of TAs that are very helpful also. Please post questions. If you feel that, no, I don't understand this assignment very well, you can send a message on the group or to me, and we'll arrange a one-to-one session. We are ready to do that. But we can have a half an hour session with you trying to explain something to you. If there is a particular assignment which you're finding it difficult, please feel free to reach out. No, I don't understand. I need a half an hour session on this, half an hour, 1 hour. The TS will be happy to oblige. Okay. So, but that initiative has to come from you. You're completely new to semiconductors. I don't know much. I really like the field. How should someone like me start preparing eventually to get into industry? Yeah, it's new to, I mean, all of us, right? I mean, it's okay. You keep, at some point, if all of us were in the same situation, it is new. You keep learning and keep growing. Over time, it comes. There's a very nice statement that I, rather one quote that I like very much. It seems 25% of whatever you know, you learn from your, let's say your parents and your teachers and all that, right? Something you learn by putting effort. Another 25%. Another 25% you learn maybe from textbooks or something like that, right? And then the last 25% of it is essentially with time. You can't hurry up. You have to put in effort, and it will take some time. You can't expect that within 3 months I'll become an expert in this field. These things, lakhs of engineers, scientists across the world with lots of money have put in. They have learned a lot of things over the last 70 years. You can't imagine that you're going to learn all of it in a span of months. Even if you spend years and decades on this, you'll only be scratching the surface. This knowledge is endless, right? It's okay. You keep learning. Every day you keep learning a little bit. Try to understand and read a little bit more. If you're especially interested in industries, I would encourage you to read these blogs. There are a lot of tech blogs right nowadays, right? For example, semi-analysis, semi-engineering, so many things are there which keep talking about what is happening in the world of semiconductors. Okay? So keep following some of these blogs online. You will understand what they are discussing, where the future is going, right? That's a very important thing. Okay? Their LinkedIn posts, people post a lot of interesting, ideas are being discussed across the world. It only is up to you how much you want to spend time on that. Yeah. Okay. Okay, guys. Anything else? Nikhil?
Sir, there's a question on YouTube chat, sir.
YouTube chat. Okay. Sorry, I did that. Okay. Okay, let me pick that, or one of you can read it. I think these guys don't know where even I don't know where the YouTube thing is.
Yes.
Yeah, form link, YouTube link. Okay.
I have just posted the link on chat, sir.
Yeah, I got it. Wow. Okay. What is this? Good evening. Sudarshan is asking. Understand your courses and will it be useful for research topic? These are all please TS. No, what? 1 second. I recently saw a JRF position on developing 2D materials. Well, those are. See, you better get in touch with the professor, right, who posted this position so that you can understand more about it, whether it is what is being expected. Understand my courses. There are 2 courses, yes. Yeah, semiconductor devices is a basic fundamental course. Nano and quantum photonics is more of research. There are many courses on semiconductor devices. I mean, for example, Professor Shenoy does a way better job than me, I think. But it's more of optoelectronics. Again, there are other courses where you'll find some overlaps and all that. But nano and quantum photonics, I don't think you will find so many courses. That's more of a research course. Did I answer you, Sudarshan? Please, TA guys, it's important. Okay, fine. Right? Did I answer these questions now? I think so. Yeah. Okay. Live chat. Join the conversation now. Can you give me guidance? Also, can you share any future available JRF under my guidance? Yeah, there will be some JRF positions that are under. We will announce it shortly. We have a project on that. But that is only for I mean, the idea is that you will eventually join a PhD program. Okay, more on nano and quantum photonics kind of devices, photonic integrated circuits. Yeah, there will be some position that we will announce in the next. By December round, definitely we will be taking somebody. Yeah, I think I answered these questions. Okay. Yes, you do well in the course, my friend. I'll definitely watch out. Yeah. Okay. Anything else? If not, can we sign out? We'll again rejoin back in 10 minutes. NPTEL team? I'm sorry, who was on the team? I'm sorry.
Yeah, sure, sir. This is Srinivasan from NPTEL.
Srinivasan, yeah. So I'll sign out of this. I'll rejoin back in the other link in 5 minutes.
Yeah, sure, sir. I will also end the stream, sir.
Thank you. Thank you very much.
Thank you, sir. Thank you.
Thank you, sir. Thank you, sir.
Thank you very much, Sharat. Thank you.